Hey everyone, and welcome. Today, we are diving deep into the language of motion. You can think of it as the secret toolkit physicists use to describe pretty much everything, from a car hitting the gas to a planet circling the sun. And by the end of this, that toolkit is going to be yours.
So, to get us started, I've got a little riddle for you. What do a butterfly, a speeding car, and a planet all have in common? It might seem random, but the answer is actually the key to how our entire universe works.
You got it. The answer is motion. Every single one of them is moving. And in this explainer, we're going to build out that toolkit I mentioned so you can describe exactly how they're moving with total precision.
Let's start with the absolute foundation. What even is motion? Well, the official definition is a change in an object's position over time. Sounds simple, right? But trust me, this one idea is the bedrock for everything else we're going to talk about.
But motion is a pretty broad term. To be more useful, we've got to get specific. So let's look at what I like to call the 4 flavors of motion. Each one describes a totally different way something can move.
First up, we've got the simplest flavor, translational motion. This is basically just moving in a straight line from point A to point B. Think about a car driving down a perfectly straight highway. That's it.
Okay, next is random motion. This is movement that's all over the place, with no predictable path. The perfect example is a butterfly fluttering around a garden. You have no idea where it's going to go next. And believe it or not, this is also how tiny gas molecules are moving in the air all around you.
Then there's oscillatory motion. This is that classic, rhythmic, back-and-forth movement around a central point. A grandfather clock's pendulum is the perfect picture of this, but so is a vibrating guitar string.
And our final flavor is rotational motion. Pretty straightforward, right? This is when an object spins around a central line, or an axis. Think of a spinning basketball on your finger, the blades of a fan, or even our own planet Earth spinning once a day.
So, we've got our 4 flavors of motion down. The next piece of our toolkit is figuring out how to actually measure it. And that brings us to 2 really important ideas that people mix up all the time: distance and displacement.
Now, this is a super important distinction in physics, the difference between scalars and vectors. A scalar, like distance, is just a number. It's an amount. But a vector, like displacement, has that amount and a direction. This isn't just some boring textbook stuff. It's absolutely vital for everything from flying a plane to programming your phone's GPS. Let's look at an example.
Okay, let's picture a car trip from Ikoi to Lekki. The car can't just go in a straight line, right? It has to follow the roads, make turns, maybe even go around a roundabout. The entire path it takes, every single meter the wheels roll, that's the distance. So if we checked the car's odometer at the end of the trip, it might say 1,550 meters. That number is the total distance. It tells us how far the car drove, but it doesn't really tell us where it ended up compared to where it started.
But displacement? That's totally different. It's the as the crow flies measurement. It doesn't care about the winding roads at all. It's just the shortest straight line path from the start point to the end point. And as you can see, it's a much shorter trip.
Now that we've got that whole distance versus displacement thing down, we can use that exact same logic for how we measure how fast something is moving. And this brings us to another classic pair, speed and velocity.
So here's the deal. Speed is our scalar and velocity is our vector. Think about the speedometer in your car. It tells you your speed, how fast you're going, but it doesn't tell you your velocity, because it has no idea what direction you're headed. For velocity, you need your speedometer and a compass.
So officially, speed is just the distance you cover divided by the time it took you to cover it. It's a calculation we do in our heads all the time, right? If it takes you 20 minutes to walk a mile, you can figure out your walking speed.
Let's do a quick one. If a super fast train travels 100 kilometers in just 30 minutes, what's its average speed? Well, you just divide the distance by the time, and you get a whopping 200 kilometers per hour.
So far, everything's been moving at a nice, steady rate. But in the real world, that almost never happens. Things speed up, they slow down, a race car launches off the starting line, a plane touches down on the runway. For that, we need the final tool in our motion toolkit, acceleration.
Now, this is a really important point, so listen up. Most people think acceleration just means speeding up, but in physics, it's any change in velocity. And remember, velocity is a vector. It has speed and direction. So, speeding up is acceleration. Slowing down is acceleration. And even turning a corner at a constant speed is acceleration because your direction is changing.
All right, let's try out the Ferrari challenge. Let's break down what we know. 1. The car starts from a dead stop, so its initial velocity is 0. 2. It gets up to a final velocity of 30 meters per second. And 3. It takes 180 seconds to do it. We have all the pieces we need to figure out its acceleration.
Do the math, and the answer is about 0.167 meters per second squared. Now, I know that unit looks a little weird. Meters per second squared? All it really means is that for every second that goes by, the Ferrari's speed increases by 0.167 meters per second. See? Not so complicated.
And of course, it works the other way too. When you hit the brakes, your initial velocity is high and your final velocity is low. We call that deceleration, and it's really just a negative acceleration.
And there you have it, your complete motion toolkit. We've got the basic idea of motion, the 4 different flavors, the huge difference between scalars and vectors, and our key measurements: distance, displacement, speed, velocity, and acceleration. You now have the language to precisely describe the movement of anything in the universe.
But we're not quite done. We've totally mastered the what and the how of motion, but we've left out the biggest question of all, the why. What is that invisible push or pull that causes an object to accelerate? What makes things move in the first place? Well, the answer to that is forces. And that's exactly what we'll be diving into in our next explainer. Thanks for watching.